afternoon. I'm Dave Cancam. I serve as the University Affairs Officer here at Center Glenn. It's my pleasure today to have one of our upcoming researchers join us today to speak on the last but fourth topic, which is materials and structures for extreme environments. And our speaker today is Dr. Lee Kohlman, whose affiliation with this center goes back many years when he served as one of our graduate fellows in a NASA sponsorship. His performance since then has been so stellar, even through the time he was a graduate student, that he was actually recruited as a full-time employee before he completed his PhD work. Currently, he works on the area of machines and aerospace systems, specifically in the area of hybrid and turboelectric aircraft propulsion. In that capacity, Lee develops superconducting stator designs, test methods, as well as test hardware. He also investigates cryogenically cooled components for turboelectric power and power propulsion system concepts. Lee obtained his master's in physics from the University of Akron in 2008. Subsequently followed that to obtain his PhD in engineering from the same university. We're certainly fortunate and very delighted to have Dr. Kohlman present to you this afternoon. So at this point, I'll call on Dr. Kohlman to make his presentation to you. If you have any questions, you can see below my portrait there the website. You can send in your questions and we'll respond to them later on at the end of this presentation. Thank you. Dr. Kohlman.
Thank you, Dr. Cancam. Today I'd like to present an overview of some of the work that we're doing in the Materials and Structures Division, in particular with a focus on applications of various materials research to electric aircraft and aircraft in general. So we can go ahead and start the slides. There we go. So as I mentioned, this is really a look at some of the advanced research in materials and structures, and in particular for extreme environments. So what is an extreme environment? Basically, this is anywhere where the requirements of the application put extremely limit your selection of materials. So examples might be in aeronautics, engine aircraft components and sensors. It may be aircraft structures such as wings and fuselage structures. And then also we're investigating new aircraft power and propulsion system components. And there's a lot of very strict requirements that are put in place. Also, a variety of application areas in space, such as propulsion systems, primary structures, insulation systems, tank structures, active components and structures, and thermal protection systems. And this, of course, is not a complete list, but just some of the highlights in some of those areas that we're working within the Materials and Structures Division here at Glenn. The pictures that I have on this slide, the top one shows a GE Gen X engine, and this is a good example of a variety of Glenn technologies and areas that we're working. So you can see at the back end of the engine, toward the X, there's some little chevrons back there. This was a Glenn-led technology development project in the area of acoustics. Additional work related specifically to this structure is looking at the use of shape memory alloys as an actuation mechanism to actually move those little chevrons on the back of the engine. Other areas with just this image is the large fan in the front of the engine. We're we're working a variety of technologies looking at composite fan blades and impact tolerance during bird ingestion events, and also the structure that you can't see in this picture but surrounds the fan that has to, in the event of a blade failure, contain that blade and prevent damage to the aircraft. Other technologies include materials inside the combustor of the engine, and I'll show some work related to that later. The picture toward the middle shows a spacecraft on reentry. Another area that we're investigating is materials for thermal protection systems. So these have to be very durable. They have to take a very high heat flux, and hold up during atmospheric reentry and protect the payload. And in some cases, that payload is going to be human beings. So it's very important that we understand how to make those materials, how to inspect those materials for flaws, and how to properly design those materials for that application. And then the third picture here shows some work in the area of compliant tires. So if we want to send a vehicle to Mars that has a significant amount of weight to it, we need to be able to carry that weight over very rough terrain, and so we need some sort of a compliant tire, but something that doesn't have air in it because we don't want to have to worry about getting it flat. So these tires are an example of work that's been done here to develop spring tires. So these are tires literally made of hundreds and hundreds of small springs, carry a lot of load, and can conform to a rough terrain. Some examples of some different conditions that could be considered extreme or extreme environments would be high and low temperatures, such as atmospheric reentry, where you're in the thousands of degrees. Low could include cryogenic temperatures, both in space and then also potentially in new and emerging systems such as superconductors and cryogenic fueled aircraft. And then also cyclical temperatures, so components that have to see repeated heating and cooling cycles can experience a significant amount of fatigue. Also high stress, high strain, impact loading. They sometimes have to survive in an oxidizing environment at high temperature, in vacuum. Sometimes there's requirements on outgassing in a vacuum. For example, things that go onto the space station, you have to be very careful that they don't have volatile organic chemicals that basically get into the atmosphere, because you can't easily you can't get rid of it. You can't open a window and simply get rid of it. So things have to be tested for off-gassing. And then also things exposed to the vacuum of space or oxygen in space. Also high current in the case of conductors, or high voltage power electronics, for example. And then also radiation is a concern for both space and also atmosphere, within the atmosphere. So aircraft flying at high altitude, say 30,000 feet, 35,000 feet, 40,000 feet, experience a much higher radiation flux due to cosmic rays hitting the upper atmosphere. So this can actually damage and disrupt electronics and other power devices. And then most of the time, these applications end up including many of these different types of requirements, and in any and all combinations, and then many more that I haven't listed here. Some of the pictures I've shown on this slide represent some of our work for extreme environments. The top image shows is an example of some of the work we do in alloy development for rocket engine combustors and nozzles. The picture toward the middle shows a ceramic coating on a superalloy turbine blade. So this is an oxidation coating to prevent the blade from eroding during operation. And then the image to the bottom right shows an example of a ceramic matrix composite component that's being designed to tolerate the much higher temperatures that we're trying to achieve within the engine core. So there's two main approaches that are taken when it comes to development of new technology. And as part of this design challenge, many of you are going to be really approaching this from the top down, or the tech pole. So in this case, we would look at the top level application, so assessing the requirements of the application, and from there we would assess potential design solutions and then derive material requirements. Then we're going to want to look at potential existing material solutions, and then from there identify gaps in performance or gaps in understanding of the response of either the structure or the material. So many times there are actually materials that have been developed a long time ago that have been certified through almost a brute force approach. In particular with composites, this tends to be true. But the detailed understanding of that material in, say, a new application such as during an impact, if that material has to, say, contain a fan blade because it's being used in the fan containment structure on a jet engine, we might not necessarily have a complete understanding of that dynamic response and how the material fails. And then we want to, basically, once we understand what we don't know or what we don't have, we want to set to developing new methods for design or analysis or characterization, and then also potentially design new materials to meet the requirements as needed. Once we do that, then we have to then certify that new material or method or analysis technique, and then ultimately we can then apply the new technology. The bottom-up approach, or the tech push sort of approach, is sort of the opposite. So in this way, we would investigate the fundamental characteristics of the materials and structures. So we're looking at the underlying physics and trying to understand better the underlying physics of how the material responds in certain extreme environments. And then from there, we want to use that new understanding to identify opportunities to apply some of these new technologies, to do something new or do something old in a better way. From there, we would determine any sort of gaps or shortfalls in the new technology, and then refine it, and then ultimately apply it to a new application. So the picture on the right actually shows an SEM image of a silicon carbide fiber that's being developed for ceramic matrix composites for use in jet engine applications. The image on the bottom right shows is an example of a digital image correlation technique being used on a rotating shaft at high speed using a pulsed LED illumination system paired with a very high resolution camera set. So this allows us to actually look at deformation of the shaft during operation and look at the local strains induced by torque loading, and also look at any sort of distortions or development of damage during operation. So the Materials and Structures Division does both of these approaches, both from the high level and the low level, or the top down, as well as the bottom up approach. So we've got work in smart alloys, high temperature alloys, ceramic and polymer composites. But then we also look at the higher levels, structural dynamics, structural mechanics, to make sure that we understand how to properly design with these new materials and to incorporate some of the new advances in design methodology. So this slide shows a wide variety of different work in different areas that's being performed in the Materials and Structures Division. Starting at the top left, high temperature materials. As I mentioned before, ceramic matrix composites is a big area of investigation. This allows us to get much higher temperatures in the turbine core, which ultimately helps us achieve higher turbine efficiency and cuts down our fuel usage during flight. This also includes things like protective coatings for the CMCs, so you have to make sure that the CMC doesn't oxidize or erode. And then also a lot of work in more kind of conventional metallic components, looking at super alloys, single crystal alloys, and looking at the bonding of, in this case, the small image in that top left box with the green turbine blades, looking at how we make the attachment between one type of super alloy for the disc and the turbine blades on the outside edge. In the center is a couple of different examples of some of our lightweight composite concepts, or lightweight concepts. The top image in the top left image in that box shows a hybrid composite gear. So this is a technology that's being developed to help reduce the weight of drive systems in vertical lift vehicles or in helicopters. The idea here is, rather than making an all metal gear, we want to replace the web portion that primarily takes a torsion load and replace it with a much lighter weight, high stiffness carbon fiber composite. Some additional work in lightweight composites, looking at nanotube applications in composites, nanotube yarn development. Also looking at aerogels for lightweight insulation. Possible applications include cryogenic tank insulation, refrigeration type insulation, and possibly even insulation in your home. And then also looking at sort of structural concepts that are applied to sort of a material level. So this is an example of a lattice structure that would replace a conventional thick panel or sandwich panel. And these can be tailored to have different, by tailoring the lattice structure, you can tailor the stiffness and the strength in different directions. And you may even be able to functionalize these materials by using shape memory alloys, for example, and actually have a lattice block structure, a finely designed or finely engineered structure that's capable of changing shape. So one possible application of something like this would be having shape-changing wings on an aircraft that are tailored to give you high lift at takeoff, but then are able to change shape during flight to reduce drag. The next category is the power system materials, the box on the top right. So some of the different areas we're looking here is focusing on motors, motor topologies, motor designs, motor materials. So we're looking at kind of rethinking how we build and design a motor in the context of an aircraft. So induction motors were invented over 100 years ago, and they really haven't changed all that much in terms of how they're manufactured and how they're built. So we want to kind of revisit that and see if we can apply some of the new technologies and new analysis methods to these to sort of an old technology, and see if we can squeeze some more efficiency and power density out of it. We're also looking at superconductors and the application of superconductors to potentially aircraft applications. So superconductors allow us to get a much higher efficiency than we can with a conventional conductor, and potentially a much higher power density. However, there are still challenges with superconductors. They tend to only like to operate in a DC environment, and when subjected to AC fields, do still generate loss. There's zero, by definition, a superconductor has zero DC resistance when it's below its transition temperature. But if you have an AC field on it, it still does produce losses through a variety of mechanisms, eddy current losses, hysteresis losses, and such. So there's work going on in that area to attempt to reduce that loss to make it useful in a stator. We're also looking at lightweight cable transmission or power transmission cables, and also sensor cables. So looking at carbon nanotubes, for example, as a conductive element in a cable rather than copper, to just get the weight out of those lines. So even in a non-electric propulsion type aircraft, there's miles and miles of sensor wires. So if we can reduce the weight of those sensor wires and keep them durable to make sure that they're not going to be damaged, we can potentially save a lot of weight on the aircraft, and then either get more payload or better fuel efficiency. Also looking at solid oxide fuel cell materials, membrane materials, to help enable potentially new ways of generating power on the aircraft or on a space vehicle. The box to the bottom left, mechanisms and drive systems. There's a variety of work here. So there's definitely some overlap between the lightweight concepts, for example, the hybrid composite gear, and then our gear, more traditional gear technology research. So we're researching the gear area focuses on new gear designs, making gears more efficient, potentially addressing things like high windage and high-speed gears, but then also some of the failure mechanisms in the gears, such as pitting and spalling that we see under very highly loaded gear sets that appear in rotorcraft transmissions, for example. But then also looking at the impact of certain requirements on the finishing of the gears. So a lot of gear design in rotorcraft transmissions is actually dependent on a condition known as oil out. So you have to be able to tolerate shutting off oil to the engine for a certain amount of time, basically long enough to be able to save the vehicle. So this is an area of ongoing research. You know, how do you make a gear tolerant to not running with oil? A couple other things in this area, kind of talked about it before, the spring tire, and then also the acoustic chevrons on the back end of the engines, and actuating those to be able to control the noise and the efficiency of the engine. And then also deployable structures, so large solar arrays for space, antenna structures, and potentially other sorts of space structures. And then computational modeling, there's continuous development, looking at how we capture the physics of the materials and certain phenomena, and appropriately model it so that we have confidence that what the computer is telling us is actually what is going to happen. So there's various modeling efforts in shape memory alloys, looking at how those actually respond to certain load states. Modeling efforts in composite materials, looking at how the fibers interact with the matrix materials. And then also modeling efforts on turbines, looking at CFD, for example. And then the last category here, flight structures. So kind of this stepping up from a lot of the more fundamental work to actually large structures. So we're looking at basically vibration testing and perform vibration testing of large large components, including some work for the Orion. Also looking at fairing jettison, basically looking at the dynamics of that detachment, and then also large composite structures, including tanks for space vehicles, and also composite fairings, for example. So the importance of materials in aircraft systems. So there's a variety of different systems on an aircraft, and all of these have some sort of dependence on material characteristics. So your structural systems, these might include your wing skins, your fuselage, your tanks, your landing gear. These basically all have to perform a function carrying some sort of mechanical load. And generally, they're going to also have to perform some other function at the same time. But primarily, they're going to be some sort of a mechanical device. You also have your electrical systems, so this could include your avionics, your actuation, or your actuators for flight control surfaces, but then also your entertainment systems, and as aircraft are moving toward more and more electrical power, they're starting to use electrical for the HVAC systems, for example. So the recent 787 has switched over from using bleed air in the engine to power a lot of these systems, and hydraulics to power a lot of these systems, to a more electric approach on the order of 1.5 megawatts on the aircraft. So this is dramatically more electrical power than any aircraft before it. And what they've seen is going to more electric allows the engine to perform more efficiently, because bleed air is a very expensive way to power components. You've also got the hydraulic systems on more traditional aircraft. So this would include actuators, but then you're also going to have pumps and lines and valves and things in there. And all of these things are going to rely on the properties of those materials. For example, in the pump, you're going to have a bearing, and that bearing is going to have to perform for a certain amount of time. So the selection of the bearing of the materials that go into making that bearing are going to be very important to limit wear and long life. But then also there's going to be methods that are going to try to detect failure. In the example of gears, which could be sort of considered a hydraulic case, you've got an oil that's being used to both lubricate and cool the gears. So there's different techniques that are being developed to identify particulate matter in the fluid stream that indicates some sort of a failure of the gear surface. You also have the thermal systems. You've got cabin heating and cooling, but then you've also got parasitic heat. So parasitic heat is a growing concern, particularly for hybrid electric or turboelectric aircraft, and I'll talk a little bit more about what those terms mean later. But basically, you move toward more electric systems. You have more components producing a low-grade heat or heat at a very low temperature relative to the surrounding environment. And it tends to be more difficult to get rid of heat the less delta T you have. So this is an area of ongoing research as well. Then you've got acoustics. So you may have noise damping panels. You've got engine liners that are going to attenuate engine noise. And in addition to being, for example, a noise damping panel, it may also serve a structural purpose. It may also have certain requirements on flammability. So there's going to be a wide variety of things that have to be taken into account when selecting materials for any one of these systems that may include other kind of other characteristics. And then the final systems you could think about are the aesthetic materials. So your selection of materials for the seats, the wall panels, the floor coverings, windows, anything that's basically there to kind of for the passenger, things that are really there to make their experience better during flight. So this is often something that's overlooked, I feel, by kind of the traditional engineers, and sometimes comes as an afterthought. But ultimately, if we're designing an aircraft for people to be transported on, we have to also at some point think about their experience on the vehicle and the way that they interact with the vehicle as well. So this might lead us to select different materials, and if we can make those materials multifunctional, that's where we can start to get real weight savings and efficiency. So for example, if your wall panel is at the same time has a surface treatment that makes it aesthetically appealing, it may also be able to dampen noise, and it may also serve as insulation, thermal insulation. It may have embedded, say, electrical wiring for power transmission, and it may also serve a structural function. So some different current challenges, more electric aircraft, including electric propulsion, looking at materials for lighter weight motors and generators, looking at materials used in cables, looking at materials in batteries, and also power electronics. Also looking at more efficient, higher temperature engines. So this would include, as I mentioned before, ceramic matrix composites for higher temperature turbine blades, combustor liners, and also higher strength alloys to deal with the high turbine stresses. And then also composite primary structure. So this might include requirements of impact tolerance, as well as easily detectable flaws. Anytime you build something with a material, you have the potential for off-nominal performance. So you have to either be able to account for the severity of the degradation of performance of a flaw that you cannot detect, or you have to be able to detect that flaw in some way. Also, you have to consider things like lightning strike at some point, and also thermomechanical cycling, moisture tolerance in the case of composites particularly, and then also ensuring that your analysis and prediction methods are robust enough that they could potentially be used to aid in certification. So why electric propulsion? This is one of many different options, but it allows us to basically significantly open up the design space. So there's really two main reasons we want to pursue an electric aircraft or electric aircraft propulsion. First one, of course, is do something better by doing it in a different way. We don't want to recreate the turbine engine with motors and batteries and such, because it's really hard to match the energy storage performance of fuel and the energy conversion and the conversion of that fuel to propulsive power in an aircraft for what a turbofan engine can do. They're very, very good at what they do. So we want to look at electric propulsion as a means to do something different, either in a new way or a new mission or a new configuration. Also, it allows us to integrate the propulsion system with the airframe in a different way. So in a traditional aircraft like the one that's basically laid out here, one thing that we could think about doing is adding a propulsor to the tail of the aircraft to ingest the boundary layer from the fuselage. So this has the potential to reduce the drag of the aircraft in flight. This is more or less a conventional configuration, but it allows us to move power back and forth between the two engines and to the tail. And provides us some flexibility in that, and also some tolerance to failure. And then the second reason we would want to look at electric aircraft propulsion would be to change the source of the energy. So, for example, we might use a renewable energy source on the ground, wind power, solar power, to achieve a carbon reduction by charging batteries and then flying the vehicle off of batteries. So I mentioned these terms a little bit earlier, but wanted to go back and kind of clarify these. So hybrid electric powertrain basically uses multiple sources of power. You're combining battery, energy stored in a battery with energy stored in a fuel, for example. This diagram basically represents a series, what's so-called series parallel partial hybrid. So this allows us to basically extract energy from the fuel in the turbofan, provide thrust with the fan, and then we're also generating electrical power, putting it onto a bus, supplementing that with a battery, and then distributing that electrical energy to a variety of propulsors that are motor driven in different areas of the aircraft. One reason you may want to do this is to put for example, wingtip propulsors that you can use to reduce induced drag by basically changing the vortex at the wingtip. And there's a variety of other reasons you might want to explore this area, in that it does allow you to do some potentially green charging or use renewables to offset some of the fuel load. Another way would be all electric. This is sort of the simplest of them. All of your energy is stored in a battery. It's put onto an electrical bus and then fed to a motor, and then that motor provides your propulsion. It could be one or many different propulsors on the vehicle. One of the challenges with all electric is going to be the energy storage, so the energy density or specific energy of the battery, as well as the specific power of the battery. So there's a lot of ongoing research in battery technology for ground vehicles. However, they're not necessarily compatible with the requirements of an aircraft. During takeoff, you might need a very high power level, so you might design a battery differently for that case, and you might actually sacrifice energy density to get that small, short burst of power. But if you're relying on battery power or battery stored energy for the entire duration of your flight, such as an all-electric vehicle, you may want to design the battery to favor energy density instead. So there are a lot of considerations on exactly what the battery looks like, what the chemistry is, and that needs to be considered. Also, you have the turboelectric systems. And this basically relies on the fuel to derive the bulk of your energy. In this case, this would be a partially turboelectric. You're not using battery other than perhaps for stabilization of the electrical bus. But in this case, you're using the turbofan to provide some propulsion, and then the generator is distributing some of that energy to additional motors that drive extra fans. So this is very similar to the series parallel hybrid, except you don't have the battery pack that needs to be charged after your flight. So an all-turbo electric, basically you get rid of that fan, and now you can put your engine core wherever you want. So one of the tricks, or one of the tricky parts with a helicopter, for example, is that the engine is embedded in the fuselage. It's right below the rotor, so it's seeing a lot of very dirty air inflow. So dirty in the sense of turbulent, unsteady sort of flow states at the inlet. This basically makes the design of those engines a bit more challenging, and it's harder to hit the efficiency numbers that you could get if you were to have that engine core out in the free airstream where it's seeing very nice, clean inflow. But the all-turbo electric approach may allow you to put the core where you need it or where you want it, and then put your propulsors wherever you need or want those. So there's a variety of different configurations, really kind of an overabundance of configurations that you could consider for a turbo electric. And this just shows, this is just kind of a chart attempting to capture some of the different trades that we would consider by going to hybrid electric or electrified vehicles. So you might look at different degrees of propulsion airframe integration. You may then look at different percentages of electrical energy storage as a fraction of propulsive power, and then you may be looking at the fraction of the turboelectric conversion, or the amount of energy derived from fuel. And by changing these different options, you get different configurations of the vehicle. All right, so some of the main challenges with electric aircraft and things to consider during the design competition would be that a turbine engine driving a fan is very efficient. So anytime you look at replacing a shaft with electric machines, electronics, it's going to add weight, it's going to add losses and complexity. So there must be a benefit at the aircraft level to warrant the use of the electric propulsion. And this is can be very challenging because you're going to take a penalty on the propulsion system. So you have to consider the overall vehicle. And in some cases, you have to consider a box well beyond the vehicle. You may have to consider ground operations, how you're charging a battery. So it's a very complex problem, and definitely an area of ongoing research, both with industry as well as at NASA. And then the flexibility that electric propulsion creates opens up the design space so dramatically that sometimes there's just too many options. There's too many different ways to do things. So it can be sometimes overwhelming and hard to narrow down to certain concepts. And then third big thing is that the electrical components that are available today mostly haven't needed to meet weight and durability requirements. With the development of the 787, that's becoming a little bit, there's becoming some more availability of components and some certification bias for new technologies, new high power technologies for aircraft. But in general, for aircraft, we're actually limited in voltage. And one of the things that we want to do moving to electric propulsion is to get that voltage up. So that's going to be a challenge going forward, as well as meeting the weight and efficiency requirements that we would have on an all-electric aircraft or a turbo-electric aircraft. So some ongoing areas of research specific to electric propulsion, electric machines. So this is motors and generators. We're looking at advanced designs as well as magnet materials, magnetic steels, conductors, so looking at adding carbon nanotubes to copper for conductors, for example. Also thermal management, looking at two-phase cooling, looking at high conductivity insulations or high thermal conductivity insulation or electrical insulators. And then also looking at superconductors. So we're looking at YBCO, tapes, and also magnesium diboride superconductors that can be manufactured in a way that reduces their AC losses. But superconductors have to operate typically at very low temperatures. High TC superconductors, YBCO, has to operate at below at least 77 Kelvin, or the boiling point of liquid nitrogen. Magnesium diboride wires typically have to operate at liquid hydrogen type temperatures. So you're going to either need a cryo cooler on board, or you're going to need hydrogen as your fuel in the case of MgB2, or a magnesium diboride. We're also looking at power electronics. So again, there's a lot of design considerations that are different when moving to an aircraft. We're also looking at wide bandgap semiconductors. So this includes things like gallium nitride and silicon carbide. So these devices allow us to operate at a higher efficiency than conventional silicon, and also a increased power density. So the devices themselves are smaller and can handle a lot more power while producing less heat. But we still have to get rid of that heat, and that's where the design comes in, and also things like cryogenic cooling potentially that have shown potential to improve device performance at low temperature. Also looking at inductors and capacitors in the power electronics, and also control approaches and design topologies. So in an aircraft where a motor is driving your propulsion, your primary propulsion, the power electronics that are driving that have to be fault tolerant or failure tolerant, or be designed in such a way that they can operate with degraded performance. Because you don't want to have a single switch fail, which is actually has a fairly high probability, particularly compared to conventional, say, gas turbine propulsion. You may have operating lifespans of 30,000 hours between overhaul on an aircraft engine. It's going to be very difficult to meet those sorts of failure intervals on an inverter. So you have to be able to design it in such a way that it doesn't take down your aircraft, basically. Also, cables and power distribution, looking at insulators for the wires, looking again at the superconductors for power transmission, but then also fault detection. There have been accidents in the past where basically a wire was rubbing against another cable, and the insulation got worn through, and then ultimately it led to an arc that either started a fire or took out a key piece of control, or a key piece of avionics or control surface actuator, and led to the loss of the aircraft. So figuring out how we detect these faults and then recover from these faults is another area of interest. Then energy storage and conversion, this is a big area. There's a lot of work in batteries by the automotive industry. But then NASA is also looking at how we integrate those batteries. Can we, for example, achieve a multifunctional purpose with the batteries in actually having them serve a structural purpose? Then also superconducting magnetic energy storage, or SMES, flywheels potentially, fuel cells, and a variety of other technologies. And then also thermal management. We want to look at how do we get the heat out of these components, the power electronics, the motors. It's very low-grade heat. We don't want to have big air-cooled heat exchangers hanging off the aircraft. It's going to add a lot of weight. It's going to add volume. It's going to add drag. So we want to look at how do we handle this low-grade heat. So some of the options include cryo coolers for the superconductors, but then you have to dump that heat somewhere else. Cryogenic fuel cooling, and then also looking at thermally conductive insulators, and even in some cases something like a silicon carbide switch, you may not have to manage the heat to as low of a level, and you may be able to operate much hotter. But in doing so, sometimes you take an efficiency hit. So those sorts of trades have to be weighed. And with that, I would like to conclude the talk.
Do you have any questions, Tracy?
No.
No questions at this time? Okay.
Okay.
Thanks, Dr. Kohler. We appreciate your speaking with us today.
Thank you.
With that, we will conclude our presentation.